So, good evening. So, today we'll start the second live session of the course Transport Phenomena in Biological Systems. So, myself Srijita, I'm a PhD from IIT Guwahati, fourth year PhD. So, let's wait for or two more minutes and then we'll start. So, let's start with class. I hope my screen is visible. Then we'll go through the notes and whatever is important in this week of lecture, and then we'll do some uh, problems. Okay. So first in this week, sir has mostly talked about the mass flux, mass flow rate, momentum flux, molar flux, then mass average velocity, molar average velocity, and then it comes to Fick's law, concentration gradient, diffusion coefficient, like that. The basic equations of mass transfer, what we call. So in this week, we will learn that what kind of equations do we need to solve for calculating the concentration change in a medium, or suppose a diffusion is happening. Suppose if we want to correlate with our uh, physiological phenomena, that everything is moving from one body parts to another body parts, right? So how they are moving, how the concentration is changing. So when we eat food, right? We eat food, and the amount of energy, the amount of uh, protein, the amount of carbohydrates we get from that food, how they are degraded and by the enzymes, and how they are transferred throughout the body, whether it is what is the driving force of that, whether it is a diffusion process, whether it is a dissolution process. So how can we quantify those things? We will learn in today's class with the equations. So first, sir has talked about mostly that like what is mass concentration and molar concentration, the very basic one. So as you know that mass concentration. So from the very early of our age, we know that concentration is mass concentration or any kind of concentration which is defined, or we can tell it as density. In fluids world, we tell it as density, so you can write it as rho, and we know that it is that m by v. That means it is the mass per volume, right? So here for an element I, suppose for an element I, we are suppose defining mass concentration. Then we will define it as rho I. Okay. The unit should be kg per meter cube, as you can see from the definition, right? Mass per volume. Similarly, if we want to quantify molar concentration, we will define it as Ci. It is the naming, so it is mole per meter cube, right? Now, if we want the bulk mass concentration, if we want bulk mass concentration, then it will be rho equals to summation of rho I, all the components over from I equals to 1 to n, right? And bulk molar concentration will be similarly C equals to summation of Ci. I is varying from 1 to n, right? It is the basic definition. Next comes the what is the mass average velocity, or else first we calculate the mass fraction. So mass fraction is defined by the term Ni, or here it is Wi. So it is rho I. That means the mass concentration of that one particular element I, and the divided by the total mass concentration, right? And molar fraction is Xi equals to Ci by C, right? So this is the basic terminology you can remember, or what. So somewhere you will see that Wi is written as Ni. So don't confuse it. Okay, you just remember the definition. What is the definition? Now I will define the mass average velocity. So here velocity indicates molecular velocity, like individual molecular velocity, or as well as bulk velocity, right? So we will define average velocity. Okay. Bulk velocity is the average velocity only. Okay. So how mass velocity is defined? Here in this course, whatever parameters Sir has used, I am using this right now so that you can correlate. Otherwise, you will be confused. But different books follow different parameters, so don't confuse with them. Okay. So I am just following the Sir's notations. So mass, not mass velocity, mass average velocity. So it is important. So it is mass average velocity. Okay. It is defined as V. Suppose they are defined as V. So everywhere there is a bar you can write, or there is an arrow that defines that it is a vector or scalar, but I am not writing it every time. So you just remember, you just know that it is a vector term, right? I am not marking it every time, but in the lecture you will find it every time it is marked. Okay, so don't confuse with them. They both are same. V. So mass average velocity V equals to, what is it? It is the summation over I equals to 1 to n of, so mass average velocity, right? So it will be rho I Vi divided by total mass, right? Velocity. Similarly, if you remember, or if you can calculate, so it is defined by V star. Okay. So similarly, it will be summation of Ci Vi from I to n divided by summation of Ci. Okay. Pardon my handwriting here. I think you will be able to understand what it is. So if you do the unit, so it is rho I means kg per meter cube into V means velocity, meter per second divided by kg per meter cube. So it is the meter per second. It is velocity only, right? It is the mass average velocity, and this is the molar average velocity. Okay. Now comes the mass flux and molar flux. Also, we can define it little later. So next we will do that relative mass average velocity or relative diffusive velocity, okay, with respect to v, that will be v equals to vi minus v, and diffusive velocity with respect to v star, it will be vi minus v star. Okay, I am just revising it because I think you have already studied this. So mass average velocity we have found out, right? From here, molar average velocity and mass average velocity. Now we will define what is mass flux and molar flux. So there are three things. So mass flux with respect to static frame, molar flux with respect to mass flux with respect to the reference frame, where the reference frame is moving with mass average velocity, and with molar average velocity. Okay, so there are three things. One, so first we are doing for mass flux. Mass average, no, mass flux, sorry. Mass flux with respect to static reference frame. Okay, what it is? It will be defined as Ni equals to rho I ui. So that is the numerator of the mass average velocity, right? How it is matching? So we know mass flux. We have learned the mass flux in the previous class. That means the mass flux means is the property the amount of that property, right, divided by per unit time and per meter square, right? You have remembered. I think we have learned this in the first class itself, right? What is flux is defined in general. So what is mass flux? That means mass removed or mass generated per unit time per unit area. Excuse me, right? So if we compare the unit, so it will be kg per meter cube, meter per second. So what it is coming? Kg per meter square second. Mass per unit time per unit area, right? Excuse me. So it is your mass flux with respect to static frame, right? Next, second one is the mass reference frame, mass flux with respect to reference frame that is moving with average velocity. And third one is the reference frame that is moving with molar average velocity. Okay. So if we compare for mass and molar both together, so it will be, so we just said that mass flux for static frame is Ni equals to rho I Vi, and for molar flux with respect to static frame is capital Ni equals to Ci into Vi, right? From the molar average velocity also you can tell this, right? The numerator is Ci Vi. When it is coming to the reference frame is moving with mass average velocity, so it will change like Ji equals to rho I into Vi minus V, right? You write yourself, you will, and you write then what will be the molar one. So it will be rho I Vi minus V, right? You write it for the molar one and tell me what will be the molar flux when the reference frame is moving with respect to mass average velocity, right? Right? And so I think you have written it. So it will be Ji into Ci Vi minus V, right? When the relative mass flux or mass flux with respect to the moving when the reference frame is moving with mass average velocity, and this is the molar flux that is moving with. So if you remember, this column is for mass case and this column is for molar case, right? And now next comes the when the reference frame is moving with respect to molar average velocity. That means relative mass flux with respect to molar average velocity. So it will be Ji star equals to rho I into Vi minus V star, and it will be Ji star equals to Ci into Vi minus V star. I think you can now correlate these things. Right? So what we'll take? We'll take this one, we'll take this one, and from here and from here. These two we will not use in our lectures. Okay? So it will be the mass flux, molar flux, mass average, relative mass flux with respect to mass average velocity, and relative molar flux with respect to molar average velocity. Okay? The other two, which are not, which are like wrong, which are accordingly matched, we are not going to use this. Okay? Okay. So this is the basic one. So now from relative molar flux, Ji star equals to Ci into Vi minus V star, right? So what can we write? If we express this, it is Ci into Vi minus Ci into V star, right? And from the definition of V star, we have earlier defined it. What is V star? Molar average velocity, and how they can be written, right? So it is Ci Vi minus Ci into summation of Ci Vi I equals to 1 to n divided by summation of Ci equals to 1 to n, right? Similarly, so now it will be Ci Vi minus, so Ci and summation of Ci, what it is that? So it is the elemental concentration and the bulk concentration. What we have defined it earlier at the first page, we have defined it as the molar fraction, which is defined as Xi, right? So it will be Ci Vi minus Xi into summation from I equals to 1 to n. Also, we know that Ci Vi is nothing but this, right? Ci Vi is nothing but your molar flux. So we can write it like this: Xi summation of Ni, right? So totally it can be written as Ji star equals to Ci Vi is the molar flux, so it is Ni minus Xi, and summation of all the molar flux in a system means it is the total molar flux of the system, so it is Nt, right? I hope you are understanding it now, right? Similarly, if we do the similar things, what we will get? We will get relative mass flux Ji equals to mass flux of species I minus mass fraction, right? Wi into total mass flux, right? If we compare it with this, we can define it, right? So your job is at your home, if you forget these terms, or because all the terms are similar, but one is related to the mass of the system, one is related to the molar of the system, right? Molar mass of the system. So it is a little bit confusing. Your job, what is to be done, that at home you make a table. Okay, you make a table, make 3 columns of it. First column will be your property, right? What is mass fraction? Okay, so you define it as fraction. Mass fraction you will write Wi. For molar case you will write Xi. Okay, for the mass flux you will write rho I Vi. For molar flux you will write Ci Vi. If you compare it, if you make a table and if you compare it, it will be very easy for you to remember. Or finally, just when everything will be done, you just before exam you can just go through this. So go through this and you will remember everything. So after the course is done, after the lecture is done, you go your home, do it as an assignment. You can make your own table with all the parameters for mass, and because now I will introduce more, right? It will be more confusing. What will be the fixed law for molar concentration and what will be the fixed law for mass concentration, right? Like that way, you can definitely make a column like this, okay? So this is the basic one. Next comes here the Fick's first law. So Fick's first law. So according to Fick's first law, Ji, which is we are defining at Ji star, which is the diffusive molar flux or relative molar flux with respect to mole average velocity, right? It is proportional to the concentration gradient. Okay. What can be the example of it? Suppose you are spraying something, or you can easily relate that whenever you do puja, right, in your home, and you give some agarbatti, right? So what it does, after some time you will feel that that smell is throughout to your house, but you have given at one corner, right? But how can it go from one corner of the house to the whole house? So that is the diffusion. So because diffusion is happening, so that concentration, smell, whatever we are smell getting, that concentration is going from high to low, right? Also, if you can remember that body spray we use, right? So sometimes if at one corner of your house you use the body spray, and after some time you can smell the body spray, right? So that means that is also that body spray particles, the particles inside the body spray where you are giving it, that at that corner the concentration of that particles is very high, right? And now when they are slowly diffusing that until an equilibrium, right? So now that particles are going from high concentration zone to low concentration zone, right? So that is how the concentration gradient is created. So why we use minus sign here? Because why use minus sign here? Because it is always going from higher concentration zone to lower concentration zone, right? Similar example we can give, that if we there is a glass of water, and we are mixing an ink, right? So that blue ink, initially it was at one point, and still you can see that whole glass of water is becoming blue, right? Similar logic can be applied here, that the concentration is going from higher zone to lower zone. So that is called the diffusion. I think you have already aware of what is diffusion. So it is the same thing. It is diffusion goes from higher concentration zone to lower concentration zone, and that's why we are using the minus sign. It is a mathematical approach. So now it is proportional to the concentration gradient. So how can we write it? So it is Ji star equals to, so when we convert it from proportionality to equal to sign, we need to use a proportionality constant. So it is nothing but minus di of grad di, or you can use dci dx. Okay. So it is the concentration gradient. It is, so di is your diffusivity of I, element I, diffusivity of I in the reaction, and this is your diffusive molar flux, right? What will be the unit of it? So Ji was your diffusive molar flux, right? We have earlier defined the unit of molar flux. It is nothing but your mole per meter square per second, right? Minus di dci dx, right? Dci is molar concentration, so it will be mole per meter cube, and there is dx. Dx is meter, right? Dx is the distance. So it is coming as, so mole will cancel out, meter to the power 4 and meter square. So it will go up. So it will be meter square per second. So unit of di will be meter square per second. It is a coefficient of diffusivity. Okay. Now if we in this equation, if this equation can be placed in this equation, right? So what it is? So Ji star equals to Ni minus Xi nt, right? We have derived that. And also Ji star equals to minus Di grad Ci, right? So if we put this, minus Di grad Ci equals to Ni minus Xi nt, right? So Ni will be minus Di grad Ci plus Xi capital NT, right? So it is coming from two terms. So if we write it clearly, so Ni equals to minus Di grad Ci plus Xi nt. So this is your molar flux. This term is counting the diffusion in the system, diffusion due to the concentration gradient, and this is calculating the convection part. That means due to the flow or flow parameters, how this molar flux is changing, and this is accounting the diffusion. Similarly, if we write for mass flux, so Ni will be minus Di grad rho I plus Wi n T, right? Are you agreeing? I think it is clear now more. Right? Any question? Okay, so right, this is for mass flux. Now, if you remember, this week we are also getting to know what is continuity equation or conservation of mass. Right? So for fluid purpose, we calculate it as, we know that it is dm dt equals to reaction, input, output, generation and consumption, right? So in case of input, we can write it as d dt of m means volume, right? Rho into v. So if we consider there is a cube we are considering, and we are taking a small part of infinitesimal small part to calculate our whole continuity equation. So it will be m, that is rho, v means delta x, delta y and delta z, right? It is all the cases. And whatever is it coming from x direction to going out from the other side, we are calculating right like this. So if you go through the lecture, you will be it will be, you will clearly know what we are talking about. But I'm just now doing that. Input is, so it is also calculating its flux, right? So rho with the velocity of u is going in, and rho, the velocity of u is going out from x plus delta x direction. So this is, suppose this is x, y and z direction. So this point will be x plus delta x plus y plus delta y plus z plus delta z direction, right? And how are these changing? So it will be multiplied with the area. So for x direction, so this is x, y, z, right? This is your z, this is your y, this is your x. So for x direction, you need to calculate the yz. The area will be yz. So it will be delta y into delta z plus rho v. V is the velocity at the y direction, u is the velocity at the x direction, and w is the velocity at the z direction. Okay. So it will be rho v y minus rho v y plus delta y into delta x delta z plane, plus for the z direction it will be rho w from at z minus rho w z plus delta z from the delta x into delta y plane, right? We are calculating this for a fluid system. Then we will come to the reaction system also. Okay. So now we'll divide this with delta x, delta y and delta z. What will it will be left with? So it will be del rho del t equals to, we'll be dividing it delta x, delta y, delta z, and we'll be taking very limit that delta x will be tends to 0 because we are considering it as a infinitesimal small particle or small sphere, or sorry, small cube in a bigger particle system. Okay, so it will be minus of del rho u by del x, you remember this, plus del rho v by del x, del y, sorry, plus del rho w by del z, right? So del rho del t equals to, it will come this side, and you remember what it is, right? It is divergence of rho into v. If we write it in vector form, it will be divergence of rho v. We know that, right? So now if we expand this, del rho del t plus, if you expand this, so it will be rho into divergence of v plus v divergence grad rho equals to 0, right? Now if you remember this term and this term, if you combine these two, what you can remember, it is the definition of substantial derivative, right? Can you remember this? In the last class we have learned this, that what is total derivative, what is substantial derivative, and what is the expression for substantial derivative, right? Do you remember? If don't, go back to the lecture and come back here. So combining these two, we can write it as capital D rho dt plus rho into divergence of v equals to 0. This is for your fluid system, right? And when we say that fluid is incompressible, that means rho doesn't change with time or space, right? Rho is a constant quantity here. So if rho is constant, you can see that it will reduce to divergence of v equals to 0. If you remember, it is nothing but the continuity equation, del u del x, del u del y plus del w del z. It is very popular continuity equation, right? Now if we want to do it for concentration system, right? So concentration system, the equation will be same. This is the main equation, that accumulation in a reaction, accumulation is equal to your input of the reaction out minus output of the reaction plus generation of the reaction and minus consumption of the reaction, right? Suppose now if we are doing it for multi-component system in case of concentration, so what will be? Similarly, dm dt will be similar, del rho I del t into delta x, delta y, delta z, right? equals to generation, and we are now defining the generation with respect to the mass flux, right? It is Nix at x minus Nix at x plus delta x. So earlier we are defining with rho into u because we are considering mostly we are focusing on the fluid mechanics part or fluid property part. So we have to take the rho u there. Velocity and density are very important. But as we are changing those things to your mass problem or mass transfer problem, so we have to define everything with respect to flux, right? So it will be what? It is from the x direction, so it will be multiplied with delta y, delta z, right? Plus similarly in y at y and mass flux at y plus del y into it will be del x del z. Plus for z directional mass flux we have to write Niz at z minus Niz at z plus del z into delta x into delta y, right? And also we are considering here one extra thing, that some reaction is happening and that reaction is defined as Ri and its molecular weight. And you have to multiply it with the volume. Why? Because unit of Ri is kg per meter cube per second, right? So here it is kg per second. All the terms is about kg per second. So we have to bring it to the same unit. So we have to multiply it with the volume of the system. So if we now similarly, if we divide all the terms with respect to delta x, delta y, delta z, and we think at limit delta x tends to 0, delta y tends to 0, and delta z tends to 0, we'll get the similar type of equation. What it is? Del rho I del t. So we are bringing all these things in the left hand side. So it will be plus del Nix del x plus del Niy del y plus del Niz del z equals to Ri into Mwi, right? If you remember. So it will be, if you write in the vector form, del rho I del t plus divergence of Ni equals to Ri into its molecular weight. Now if we change this for the mass system, we have to divide it with molecular weight and we'll get del Ci del T plus divergence of Ni equals to Ri, right? Now, if we also already know that molar flux or molar flux contributes to diffusion and convection both, right? So now if we take this, so Ni we know minus di grad Ci plus Xi into Nt, right? So now if I replace this, so before replacing we can write it as minus C into di grad Xi, because Ci by C equals to Xi, we know that. So if we want to represent it in the terms of mole fraction, we can write this, right? Plus Xi into Nt. So now if we replace this in the governing equation, so what it will come? Del Ci del T plus divergence of Xi minus C di grad Xi, right? It will be equals to Ri, right? Now we will expand this. So what it will come in? Del Ci del T plus divergence of Xi into Nt, right? Before that, we will write Nt. We will know what is Nt. So Nt is the total molar flux of the system. So Nt is C into V, right? C is the bulk concentration, V is the average velocity, molar average velocity, right? Or you can write V star. V star is the molar average velocity, right? Now, so Xint, it will be Xi C V star, right? Also Xi C is elemental Ci into V star, right? Now we'll replace this in place of this. So del Ci del T, it will be plus divergence of, so Xint will be replaced by this. So it will be Ci into like molar concentration into molar average velocity. That means molar flux, right? Minus divergence of C di grad Xi minus divergence of C di grad Xi, right? These three terms, left hand side terms are completed, equals to Ry, that is the reaction. Now if we expand this, So del Ci del T plus divergence of, so it will be Ci into divergence of V star, right, plus V star divergence of grad Ci, right, minus divergence of, so Cxi you cannot, you might not change it here also, you just keep it like as it is, di grad Ci, okay, so it will be better, I guess. Where is the, okay, so better keep it like this. It is better, di grad Ci, okay, so here also it is di grad Ci, okay, so here also you have to change it. It is, I am saying that you can write it also like that, but here we don't need it. So di grad Ci. Okay. So now we have expressed this term, right? This two term is coming, and now if we compare, so di is the concentration. Sorry, di is the diffusivity, which is constant for a system. So we can write it minus di into grad square Ci, right, equals to Ri, right? So what it will be finally? So finally it will be so Ci is also incompressible for a system. That means Ci is also not changing. Okay. So if Ci is not changing with time, right? So not time explicitly, you can like, it is not steady state, obviously. Okay. Sorry. It is not steady state. So Ci is not changing with space or any spatial direction. So we are considering it as an incompressible. So that incompressible means basically that when rho I, that is density or mass concentration, is not changing, like that we have taken in earlier case, like here, like here. Not here. Yeah, this is, but in case of, we cannot call it as incompressible, but basically concentration, molar concentration is not changing in spatial direction. So that term will reduce to, so this term will no longer survive, right? This term will no longer survive. So it will be del Ci del T plus sorry, I have given a wrong information here. Sorry. Why we are negating this term? Because divergence of V is zero, as we have derived from the incompressible fluid situation, right? How can I forget this? Sorry, extremely sorry. So from the incompressible fluid situation, we have discussed that divergence of velocity is zero, right? So this term will anyway no longer survive this term. So what it is left with? So it is left with del Ci del T plus V star into divergence of Ci equals to di grad square Ci plus Ri. Okay. So first term accounts for the temporal change, which is the temporal convection, and this is your or local convection, you can say local convection. This is your convection due to velocity, convection due to velocity, right? This term is the diffusion term or diffusive term, and this term is the reaction term, right? So this total equation is your this total term is your convection, diffusion, reaction equation. Okay, this if you can remember it. Okay, so when and if there is no convection, okay, so if there is no convection due to velocity, so what the terms will left? So it will be del Ci del T equals to di grad square Ci plus Ri, right? So this is your Fick's second law. Okay. If there is no reaction, so in case of no reaction, it will be del Ci del T equals to di grad square Ci, and if it is steady state, this term will reduce to di grad square Ci equals to 0. Simple. Okay. And all the equation you can write for the mass concentration term, right? So for mass concentration term, it will be the convection diffusion reaction equation will be del rho I del T plus V divergence of rho equals to di grad square rho I plus Ri. This is a convection diffusion reaction term. Without the convection due to velocity, it will be del rho I del T equals to di grad square rho I plus Ri. Without reaction, it will be del rho I del T equals to di grad square rho I. And without steady state, it will be just simply di grad square rho I equals to 0. Okay? I think you have understood this, right? If you have any question, you can definitely comment, because I will be anyway sharing these lectures with you throughout through the Excel sheet, where you will get my classes in details in my YouTube channel. And if you have, then also if you have any question, you can definitely ask. Okay. So now we will go back to the problem solving portions, because that is ultimately important. These are the theory you need to know, and you need to do the derivation by yourself also, so that your hand will be easier while you will be doing in your exam, right? And not only in NPTEL exam I'm talking about, this type of questions may come in your GATE exam also. Okay, it is very easy to solve if you are applying for from chemical engineering background or biological background, whatever. This type of question will definitely come in your GATE question. So go through the lectures, go through my lecture sessions, my live sessions, and derive it by yourself. As I have said earlier, do it as assignment, that how the concentration and the molar, how the mass concentration and molar concentration terms are changing till this point, like till the fixed second law equation. Then you will remember these things very easily. Okay. You can just go through before lecture 1 or 2 times before giving the exam. You will easily remember everything, and do solve for yourself all these things. Okay. And also these equations will be helpful for you to model something. If you are a research student, you will be, suppose you are modeling something in biological phenomena, specifically as this course is specifically for the biological purpose. So you can, anything you can, so everything in our body is diffusion based or concentration gradient based. So you can definitely think of applying this equation in your modeling. If you do the model, if you simplify the system, you will be able to calculate this concentration profile, the velocity profile, the reaction profile, all these things. Okay, what is the diffusivity, how the diffusivity can change with respect to your experiment. Okay, and this will add value to your research paper, because experimentally one thing you are seeing, if you match these things with your simulation or with your models, and if you talk about this equation, if you explain these equations, then your paper will be more valuable and more scientific. Okay, so let's go to the question answer session. So first one is very easy, right? Identify the equation. So we have just derived the continuity equation. So it is, so if you go back, so if you go back to the continuity equation, you will remember, right? So what is del rho del T equals to divergence plus divergence of rho V equals to 0, and capital D rho dt equals to minus of rho into divergence of V. So we have done this in the lecture itself. So it will be option A and option C both. Right? Next, a bioprocess device is known to show the flow characteristics as governed by the equations below. Which of the following statements are true? So simply everything is given, and a bioprocess to happen, so we have to make sure that it is incompressible. So for incompressible, we know what is the continuity equation? So divergence of V equals to 0. So we'll take first term is del Vx del x. So it is coming as minus 2a, right? Then del Vy del y is coming as 2b, and del Vz del z is coming as minus 4c, right? Minus 4cz, right? So now if you make this, so minus 2a minus plus 2b minus 4cz equals to 0. So it will be b minus a minus 2cz equals to 0. So the design of the device is feasible when this is true. So it is option C. Next. Dalgona coffee is a coffee variety with whipped coffee layer on top of milk. In order for the layer to float on top, the coffee needs to be whipped nicely. In a partially failed attempt to make the coffee, as soon as the whipped coffee is added to the cold milk, the coffee started diffusing to the immediate layer of the milk beneath it. If its molar average velocity is 6 units, that means molar average velocity is defined. V star is 6 units across the circular layer, and the diffusion velocity of coffee with respect to V star is 9 units. That means V I minus V star is defined as 9 units. Calculate, here the downward direction is taken positive. Calculate the velocity of the diffusing species with respect to stationary. So need to calculate the VI. So VI will be VI minus, this is 6 equals to 9. So VI will be 15 units. Okay, so option B. Next. A system in a system with two components A and B at a time t equals to 0, A is being diffused into B along x direction, where starting at x equals to 0, the molecular mass fluxes are represented by Jx and Jbs respectively. Which of the following statements are true with respect to the above system? Okay. So by definition, we know that sum of diffusive mass fluxes relative to the mass average velocity across all species in a mixture must be equal to 0. Must be equal to 0. Okay. So it will be option B. Jx plus jdx equals to 0 for all t. It is defined already. Next question. The relationship between the mass flux and concentration in a binary mixture is given by. So as you can know that mass flux is Ni and it is defined by minus d rad C I. Or Ji also you can write it. It is obviously Fick's law. Next. Moisture content is an important parameter that is essential in the storage of rice grains. Right? This parameter is mainly affected by the storage temperature and relative humidity. Increased moisture content results in bacterial fungal attacks and also in insect infestation. Long-term storage of grains in the right quality is essential to ensure continuous supply of grains, especially in the times of crisis. The grains should gain or lose moisture under a set of conditions until an equilibrium is reached. The desired moisture content for storage of rice grains is below 14% dry weight. A storage facility maintains the rice stalks at a moisture content of 14%. Unexpected rain in the area increase the relative humidity, leading to increased MC of grains. Considering the movement of water across the membrane in one dimension and the gradient of MC between the inside and outside of the grain as the only driving force that increases the MC through diffusion, which among the following do we get as the governing equation if a steady state material balance is done? Cm is the concentration of water at the membrane, d effective is the effective diffusive constant. So, diffusion is happening, right? So, it will be simply concentration change is happening, it will be d effective into delta square Cm by delta x square. Del square Cm by del x square equals to 0. Or as there is no other term, no partial derivative is there, so it will be d. Or if it is steady, if it will be unsteady state, then it will be equal to del Cm del d. But as it is just steady state, we can simply apply this. So option D, option C. Next, assuming that the above process of MC gain has reached an equilibrium, identify the expression that best explains this equilibrium. So equilibrium means there is no concentration gradient, right? Equilibrium means there is no concentration gradient. So dCm dx will be 0. And we also know that J star is dependent on this minus di of dCm dx, right? So it will be 0. Simply option B. Option B. Next. The moisture gain by grains is also known to occur via diffusion through pores on the membrane. Now, only considering this mode of diffusion through large pores in effect, identify the equation that best describes permeability of the membrane with additional resistance. So, from the lecture note, we have seen that permeability P is defined as dmk diffusion coefficient by d into epsilon by tortuosity. Porosity by tortuosity, right? So it will be option A. Next. Fick's second law gives a relationship between Fick's second law, right? Rate of change of volume in the concentration gradient name, no. Rate of change of volume with concentration gradient, no, obviously. Rate of change of concentration and the velocity gradient, no. Rate of change of concentration and the concentration gradient. So it is, so Fick's law we have learned recently that it is del C del T equals to di grad square Ci, right? So it is the rate of change of concentration and the concentration gradient. Next, consider a volume element in a right-hand coordinate system as shown in the figure. Which of the following is true given that the flow is unidirectional in x direction alone and accumulation within the element is 0. So, from the continuity equation, if you apply, there is no accumulation, right? So, continuity equation is divergence of rho v equals to 0 at steady state. So, at steady state, right? So, it will be unidirectional, right? So, it will be d rho vx dx equals to 0. So, it is option B. Next. A bioprocess device is known to show the flow characteristics as governed by the equations below. Which of the following statements are true? Similarly, you have to do it for the continuity equation. Divergence of V, I have done it earlier. So del Vx del x is coming as 8ax, del Vy del y coming as 6by, del Vz del z coming as 2c. So, sorry, 4c. So it will be 8x plus 6by plus 4c equals to 0. The design is feasible when this is true. Okay, option C. Next. Fick's second law is similar question. So it is the concentration with the concentration gradient. To improve the taste and presentation of coffee, whipped cream is added on top of it in a cup. As soon as the whipped cream is added to the hot coffee, some cream started diffusing to the immediate layer of the coffee beneath it. If its molar average velocity is 5 units, so molar average velocity, similar problem, it is defined as V star equals to 5 unit. Then and the diffusion velocity of cream with respect to V star is 6 unit. That means V I minus V star equals to 6 unit. Calculate the velocity of the diffusion. Vi will be 11 unit. Next. Microgreens are considered an easy source of micronutrients. In order to cultivate microgreens, seeds are soaked in water for 1 hour prior to sowing to enable easy germination. The water enters the seed during this time, considering the movement of water across the outer seed membrane in one dimension and the gradient in moisture content between the inside and the outside of the seed as the only driving force for diffusion. Which among the following do we get as the governing equation if it is a similar kind of problem? So it will be as it is. Option B. D effective into d square c dx square equals to 0. Considering the positive x direction to be from outside the membrane to the inside of the seed, under which of the following conditions does the flux Ji star become 0 in the above scenario? So diffusive progresses in the positive direction. There is no movement of water across the membrane. An equilibrium is reached. So it is simply an equilibrium is reached. Now considering only the diffusion through the large pores on the seed membrane, satisfying the equation so P is the permeability, epsilon is the porosity and tau is the tortuosity. So epsilon is the void fraction available for diffusion. So porosity defined is void fraction, volumes of pore divided by total volume. Void fraction available for diffusion, and tortuosity tau is defined as the ratio of actual path length to membrane thickness. Okay, next. A theoretical velocity field for a liquid handling bioprocess device is proposed as this. Under what physical constant is this design realistically feasible for an incompressible fluid? Similarly, okay, so del Vx del x equals to 2k1x, del Vy del y equals to 2k2y, del Vz del z equals to 2k3z. So it will be k1 x plus k2y plus k3z. If we just add all these things, it will be just option B. Next. In a long cylinder used for formaldehyde disinfection, the mole fraction is x. The mole fraction XA is 0.2. Okay, so XA is 0.2. If the velocity of formaldehyde VA is 15 units, and the velocity of air, which is option B, VB is 5 units, what is the molar average velocity V star at this plane? So for two component systems, V star equals to VAXA plus VBXB. So it will be 15 into 0.2 plus 5 into 1 minus 0.2, that is 0.8. How much is it coming? Calculate and tell me. Very easy sum. How much it is coming? So it is 15 into 0.2 plus 5 into 0.8. That is coming as total 7. The answer is 7 units. So it is coming as 7. Answer is 7 units. Next, which mathematical expression correctly represents the substantial derivative of density, and how does it relate to the continuity equation for a fluid system? Right? So, as we know already, capital. So, I am not again doing the derivative. So, it is capital substantial derivative is equal to rho into divergence of V. Okay, it is option B. So you go through my previous questions or first derivative, then you can understand. I think by now you have already figured it out. Okay, according to Fick's first law, as applied to a stationary coordinate system, the total molar flux Ni of a species is composed of which two distinct physical mechanisms. So, as we can see that Ni is the total molar flux is summation of minus C di grad xi plus xi nt, right? It is option A. During the derivation of Fick's second law, using a shell balance approach on a membrane of thickness L, what is the result of taking the limit as the shell thickness delta x tends to 0 for a non-reacting species? So you already know these things. I am not taking it. It is del Ci del T equals to minus del Ni del X, right? It is option A. Next, in the context of the continuity equation for a single species I in a multi-component mixture with a chemical reaction, which terms represent the net production rate? So it is Ri, the reaction rate, and the molecular weight of the reaction product. Option C. Next. Sorry. Which of the following describes the relationship between the relative mass flux Ji and the absolute mass flux? So relative mass flux Ji equals to absolute mass flux minus Wi into Nt. It is option B. Next. For a binary mixture, For a binary mixture where VA and VB are species velocities, what is the diffusive velocity of species A with respect to the molar average velocity? So it is VA minus V star, option A. Next. Under steady state conditions with no chemical reactions, Fick's second law for one-dimensional diffusion reduces to which mathematical term? Under steady state and no reaction. So we have defined it. So it is del I d2ci dx2 equals to 0. Option A. Next. What is the primary physical driving force of mass flux within a single phase as used in the standard formulation of Fick's law? So it is very easy. So it is concentration gradient. Next. In a binary mixture of species A and B, the molar average velocity V star is defined as this. Prove that the sum of the diffusive molar fluxes relative to V star is 0. J is 0. So first we will prove this. Okay. So diffusive molar flux definition is what? So Ji star equals to Ci into Vi minus V, right? So for binary mixture, Ja star plus Jb star equals to CiVa minus V, here to be star plus Ci into, or Ca you can also write, Ca, this is Cb Vb minus V star, right? Now equals to CaVa plus CbVb plus minus Ca minus V star, if you common, it will come as Ca plus Cb, right? Right? So Ca minus Ca plus Cb means total C. Right? So before that we want to do one thing. So it is defined like this, right? So what is Xa? Also Xa is your Ca by Ca plus Cb and Xb is Cb by Ca plus Cb, right? So what you can expect? So V star will become Ca by Ca plus Cb into Va plus Cb into Ca plus Cb into Vb, right? So it is nothing but your CaVa plus CbVb divided by total C, right? So now if we put that in the equation, so J star plus Jb star equals to, if you put CaVa plus CbVb equals to Cv star minus, again C, total C is there, into V star, so it will be Cv star, it is coming as 0. It is proved, right? Second question was, rewrite the total molar flux relation. Show that the total flux of species A relative to a stationary coordinate frame Na can be written as the sum of the diffusive flux and the convective flux, like this. Okay, so we'll prove that. So absolute molar flux, we know it as Na equals to Ca Va, right? Also, Va equals to, if we take uh, in terms of V star we present, so it is Va minus V star plus V star, right? So Na equals to Ca into Va minus V star plus Ca V star. So Ca minus V into V star is equals to Ja star plus Ca V star, right? Also, we know that Ca equals to Xa into total C, and total molar flux Cv star equals to total molar flux equals to Na plus Nb, right? So now if you put these things, Na equals to Ja star plus Xa into Cv star, and Cv star can be written as Na plus Nb, right? It is proved. Next. Sorry. Starting from the 1D form of Fick's law for total molar flux along the z-axis is this: equimolar counter diffusion. Equimolar counter diffusion means NAZ equals to minus, or NBZ equals to minus NAZ. It is also the other way around. So now if we put this in the equation, it will be NAZ equals to minus CDAB dxa dz, right? Now if we integrate it, so it will be NAZ integration of dz from 0 to L equals to minus CDAB integration of dxa from xa0 to xal. It will come as NAZ into L equals to minus CDAB into XAL minus XA0, right? So it will be NAZ equals to CDAB by L into XA0 by XAL. This will be your final equation. Second question was diffusion of A through stagnant B. That means B is not there. That means NBZ equals to 0. So now what is the equation? NAZ equals to, if you check the equation, NAZ equals to minus CDAB dxa dz plus XA NAZ. Minus CDAB dxa dz plus XA NAZ, right? So now if we integrate it, so it will be NAZ into 1 minus XA equals to minus CDAB dxa dz. Now if we integrate it, NAZ integration of dz from 0 to L equals to minus CDAB integration of XA by 1 minus XA from XA0 to XAL. It will be NaZL equals to CDAB ln 1 minus XAL by 1 minus XA0. Okay. This is the final equation you can write. Also, you can write L in this. Right. Okay. Next. Consider steady state steady state mass transport of species A diffusing in the x direction through a stagnant medium of cross-sectional area AY and thickness delta x. Write the molar shell balance over the thin slab between x and delta x. So species A is diffusing through cross-sectional area E. So in the x direction, so it will be in AX at x minus in AX at x plus delta x into AY is the area equals to 0, right? So this will be your molar shell balance. Derive the differential equation. So if delta x tends to 0, if delta x tends to 0, it will be minus del NaX by del x equals to 0. And it will lead to simply dNax dx equals to 0. Third question is substitute Fick's law. And this we have to substitute in Fick's law. So NaX is minus CDAB by 1 minus XA into dxa dx. So this expression is given. So now dNaX minus dx equals to 0. This is the Fick's law. This is a substitution, so it will be d dx of dxa by 1 minus xa equals to 0. Oh, there is dx also, sorry. The dx. Okay. Sorry, then. So it is dxa into dx into 1 minus 1 by 1 minus xa equals to 0. This is your final equation. Okay. Next. Species A diffuses through a liquid film of thickness L and undergoes a first order chemical reaction A to B with rate Ra equals to minus K1 Ca. The governing equation, differential equation is this. Solve this ODE using the boundary conditions at Z equals to 0 and Z equals to L. Instantaneous reaction boundary condition. Okay. So, reaction is defined as this. So, T2Ca dZ2 minus K1 DAB Ca equals to 0. You can see that mostly these problems, whatever proof is there, it is most basically the algebra, basically the mathematics, right? So now if we can suppose K1 DAB equals to or root of K1 DAB equals to x. Okay. Then the equation will be D2Ca dz2 minus x square Ca equals to 0. So this has a well-known, this is ODE and this has well-known solution, which is Ca, the function of z will be C1 cos hyperbolic Az or xz plus C2 sine hyperbolic Cz, xz. Okay. So now we are putting the value. But it is there at z equals to 0, Ca equals to C0. At z equals to L, Ca equals to 0. So first condition is at z equals to 0. Now we have to calculate the concentration. Ca equals to Ca0. Right? So now I'm putting the value. So Ca at 0 or Ca0 also you can write. Ca at 0 means Ca0 equals to C1 cos hyperbolic 0. Cos hyperbolic 0 means it is 1. Cos hyperbolic 0, value of cos hyperbolic 0 is 1. Sin hyperbolic 0 is 0. So it is Ca0 equals to C1. Now we are putting the second condition. What is that? At Z equals to L, Ca equals to Ca0. So this is now 0 equals to cos hyperbolic C1 is Ca0. We have calculated cos hyperbolic XL plus C2 sin hyperbolic XL. Right now C2 can be defined as C2 is minus Ca0 cos hyperbolic xl by sin hyperbolic xl. Okay. Now, if we substitute these things, what is the questions? Okay. Now we substitute these things in the equation. So CAZ equals to CA0 cos hyperbolic xz minus CA0 cos hyperbolic xl by sin hyperbolic xl into sin hyperbolic xz. Okay. So if I simplify this, I am not simplifying it anymore. So going to the next question. Sorry. Yes. A gas mixture at 298 Kelvin and 1 atmospheric pressure consists of species A and species B. At a specific location in a diffusion cell, the mole fraction of A is 0.4. Species A is moving at a velocity of this in the z direction. Species B is moving at velocity in the z direction. Calculate the molar average velocity of the mixture. So all things are given. So simply molar average velocity will be V star equals to XA VA plus XB VB. So XA is 0.4, VA is 10 plus XB is 1 minus 0.4 is 0.6 into 4. So it is coming as 6.4 meter per second. Second question, calculate the mass fractions WA and WB and determine the mass average velocity. So first we'll calculate the mean molecular weight, which is XA into MA plus XB into MB. If you put the term 0.4 into 28 plus 0.6 into 32, it will come as 30.4 gram per mole, right? Next question, next equation is and also we know that WA is the fraction, so it is XAMA by M, so it is XA 28 by 30.4, it is coming as 0.3684 plus WB, similarly it is coming as 0.6316. So now mass average velocity will be WA VA plus WV VB. VA VB are already defined, so it is coming as, to put all the values, it is coming as 6.21 meter per second. 6.21 meter per second. Next, what is the question? Last question. Using the ideal gas law to find the total concentration C, calculate the molar diffusive flux related to molar average velocity. So ideal gas law is C equals to P by RT, right? Equals to 101,325 by 8.314 into 298. It is coming as 4040.90 mole per meter cube. Okay. Now concentration of Ca. Ca is C into Xa. Xa is defined as 0.4. So it will come as 16.36 mole per meter cube. Then molar diffusive flux JZ star will be Ca Va minus V star. So V star is given, right? V star is calculated earlier. Va is given. So 16.36 into Va is given as 10. V star we have calculated 6.4. It is coming as 58.896. It is coming as 58.896 mole per meter square second. If the values are not matching, please tell me. Okay. There are six questions. There are three more questions, I think, which I will be doing in the next class. Okay. Just to recap this session. Okay. Okay. I hope this class is helpful, and whatever problems I have done, it will be helpful for you to solve. It's all about the mathematics and the algebra and the derivation. So to feel easy with the equations and with the numbers, you have to do the derivation by your own self, so that you can easily calculate this in the time of pressure in the exam. Okay. Still, if you have any question, please comment. Okay, we'll meet on the next Tuesday with the same timing with the third week live session. Till then, goodbye. Thank you.